Ions are going to be charged particles that are either a positive or negative charge. Now, this positive or negative charge is due to the fact of an imbalance between protons and electrons. By having more electrons, they're negative. More protons, they're positive. Remember, protons are positive, electrons are negative. Now, why do I even care? Because these positive charges will become important when we start figuring out how these ions are moving through our body in later systems. Atoms that have 1 to 3 electrons in their outer valence shell. Now, a slight caveat just to make sure I'm on the same page here. That's the second shell, the third shell. Most of the main ions we're talking about in the body fall in that category. The first shell only has 2 electrons. Second and third shells both have 8 electrons as a max. So this 1 to 3 electrons, that's referring to the second or third shell of electrons. So if the outer shell has 1 to 3, it's more likely to lose those electrons than gain. It's easier to lose 1 to go down to empty, or 2 to go to empty, or 3 to go to empty, compared to trying to gain all the way up to 8 electrons. Because the ions, they're trying to become non-reactive. To do that, they need either an empty or completely full valence shell of electrons. So if you're losing electrons, that means you'll have fewer electrons compared to protons. This means that is going to be a positive charge. If you lose 1 electron, for example, there'll be a positive charge of 1. 2 electrons plus 2, 3 electrons plus 3. These will be known as cations, positively charged ions. But now if it's easier to gain, so you have 5, 6, 7 electrons in that outer valence shell. If you have 7, it's a lot easier to gain 1 to become full compared to losing all 7 of those to go empty. So in this case, if you gain 1, 7 plus 1, or 6 and you gain 2, up to 8, or 5 and you gain 3, you're now going to be negative because those are extra electrons that are there. So these are known as anions, negatively charged ions. So cations and anions are going to play a huge role in how our body balances the ions inside of our systems. Because these positive and negative charges will play a lot of impact on how you get across the membrane, how different ions move, and various other parts in our body. So here's an example showing sodium, Na, and chloride, Cl. If you notice on the sodium, there's a red electron in that outer valence shell. There's only 1, that's it. Because there's only 1, it's easier for that 1 to be given away or removed compared to gaining 7 to make it full. But at the same time, chloride here, if you count those dots in the outer valence shell, you'll see there are 7 electrons in that outer shell. Well, 7 electrons makes it easier to gain 1. So what's going to happen here is NaCl, sodium chloride, is salt. That's your table salt. What happens is that 1 single electron, so that's 1 electron right here, we're seeing now that red one has moved over to the chloride. This allows both the sodium to have an empty valence shell and be stable, as well as the chloride to have a full valence shell and be happy. This results in the sodium ending up with a positive charge because it gave away an electron, and the chloride having a negative charge because it accepted an actual electron. Together, this sharing, or this actually giving electron in this case, this allows to build the crystalline structure that is your table salt, sodium chloride. So this movement of ions, this movement of electrons is how you try to stabilize the outside rings or valence shell of the ions. And these also can be known as electrolytes. You may have heard about electrolytes or replenishing electrolytes to make sure you have your body in balance. So if you have a really heavy workout, sweating a lot, you need to make sure you replace those electrolytes. Sodium and chloride are going to be two of those electrolytes. They play a hugely important role in how our bodies function. So to go through future chapters, we'll see how much sodium and how much chloride actually does in these different systems in the future. But basically, your idea of electrolytes are going to be salts like this, sodium chloride, that can then ionize in water. So sodium breaks apart from chloride, they break apart and ionize. Free radicals. Now, free radicals, you might have heard of these before as not good in your body. Well, yes, free radicals can definitely be problematic because they can actually cause damage to your cells. But at the same time, by definition, chemical particles with an odd number of electrons. Well, isn't that sodium if it gives away its electron? Isn't that chloride if it accepts the electron? Yes, so sometimes we need these, but there are free radicals that are very dangerous to the body also. So just by pure definition, that's what it is. But a lot of times you hear people talking about free radicals or helping to get rid of them in your body, they're talking about certain types of them, not all free radicals. Chemical bonds. There's different types of chemical bonds that we'll have in our body and for that matter in nature. Electron shells, remember that ring of electrons? Those electron shells, they try to again become stable, either empty or full. So by moving an electron from one to the next, or sharing electrons, or have them bounce back and forth, this creates an energy bond between them. That's what these bonds are. So ions that are chemically inert. You see helium here, you're seeing neon. They're inert, which means they don't react because their outer valence shell is full. In the case of helium, the first valence shell fills up with 2 electrons. In the case of neon, the second valence shell is going to fill up with 8 electrons. So if they have that full 8 electrons, it doesn't want to bond, it does not want to react. But the reactive elements are ones that don't have full valence shells. For example, here you have hydrogen, 1 electron. In this case, hydrogen, it wants to either gain or get rid of, or share, or something wants to happen. Because to make this chemically inert, you would need to add a second electron to fill up that shell. So somehow you either need to fill or empty that shell. Carbon, see there's 4 different electrons in its valence shell. So carbon can actually make several different bonds. Because for carbon, you need to fill up by adding 4 more electrons out in that shell, making it have a full 8, or at least sharing to reach the 8. It's this reactivity that's going to help and fill up or make sure the electrons get stable by either filling or emptying a valence shell. So bonding. There's a little more to deal with that. We'll have to get to that later. But for now, just think about electrons. Do you have more or less electrons compared to protons, positive or negative, cation positive, anion negative? And if the valence shells aren't full, you want to either gain or remove electrons to make the ion stable. So more chemistry coming up next.